Welcome to the first video of section 6.2. In this video, we'll be discussing area under the probability distribution curves. And if we have a continuous random variable with a normal distribution, the following graphs are examples of how we can shade our probability distribution curve. In this first graph, notice we have A, and the area to the left of A is shaded. We could represent this like so. X is less than A. Whereas in this example over here, the area to the right of A is shaded. And we could represent that with our greater than sign. In our third graph here, we have the area between A and B is shaded. And how would we write that? Again, with our inequality signs. In example 6, letter A, we're asked to draw our normal probability distribution for the probability that X is less than 5 when it equals 0.65. 0.65 is greater than half 0.50. So if we have our bell curve with our mean in the very middle, we know that X is going to have to fall to the right of the mean, because the mean is the center of our distribution. Half of the data falls below our mean. We know that we want 65% of our data. So we would put 5 maybe about here. And since we have the less than sign here, we'd shade everything to the left of 5. In letter B, we're asked if the probability of X is less than 5 equals 0.65 or 65%. What is the probability that X is greater than 5? In other words, what would be the probability that our random variable would fall to the right of 5? Well, we can use the complement. And if we were asked to shade the area under the curve, I could do that with my red color here. Moving on to the next page, we have some handy calculator directions here when we are using our normal distribution. And make sure to check out the video included in this module to use our graphing calculator for our normal distribution. Inside these directions, take a minute to notice we have some exponents here, like negative 10 to the 99th power, 10 to the 99th power. These numbers just represent very, very large number values. So this is a very large negative value. This is a very large positive value. So sometimes when I'm using my calculator, I might just type in a big number like negative 1 million or positive 1 billion. You don't need to use this specific very, very small number or this specific very, very large number. Let's go ahead and look at example 7 and do one of these problems. We have a random variable with a normal distribution, a mean of 6, and a standard deviation of 2. Find the probability that X is greater than 2. And since this is a greater sign, let us use this calculator keystroke here. We're going to use our normal CDF with our X value is 2. We'll type in a very large number since x can be anything greater than 2. And then our mean is 6 and our standard deviation is 2. If we type that into our calculator, we should get about 0.9772. Let's continue with example B for when the probability of x will be less than 7 in our normal distribution. Well, since this is x is less than 7, we're going to use this keystroke right here. So let's go ahead and do that. So we're going to type in our normal CDF of a very, very small number, our random variable, our mean, and our standard deviation. We'll plug that into our calculator, and we should get 0.6915. For letter C, we're asked to find the probability that x falls between 4 and 8. So let's go ahead and use this calculator keystroke right here and type in our lower bound, our upper bound, and then don't forget your mean and your standard deviation. And we should get 0.6827. The placement of our large numbers might seem a little bit confusing to you, so let me give you a small graphical representation of each of these. For letter A, we would have our random variable 2, which would be to the left of the mean, and notice what percentage of the graph would be greater than 2? We would shade in to the right here, and that's where we got the 0.9772. For letter B, our random variable is 7, which would fall to the right of the mean, and they're asking us what's the probability that x will be less than 7, which means we would shade in everything to the left, and that's where we got about 69% of our data would be to the left. And for letter C, here's our mean. We have a lower bound of 4, we have an upper bound of 8, and we want the shaded area between these two. And that is about 0.6827. Now, for letter D, we're asked to find the maximum value of x in the bottom quartile. So first, let's look at a graphical representation of the bottom quartile. If we have our normal curve, the bottom quartile would represent the lower 25% of our graph. And we're looking for the very maximum value of x here. So in other words, they gave us that 25% of the curve is shaded in the lowest quartile. In this case, we need to use what's called our inverse norm function because we are given the area and we're actually looking for the x value. Use our inverse norm function here. So we're looking for what value will give us the lowest quartile. So we're going to use our inverse norm, and our probability to the left is 0.25 with a mean of 6, a standard deviation of 2, and this would give us a data point of 4.65. So this would mean this x value here is 4.65. That's the end of the first video to 6.2.